Hi, my name is Rob Gauna. I was a research intern at the National Institute of Standards and Technology under the U.S. Department of Commerce, and today I will be presenting on some of the results I got on my simulated experiment, subsurface structure characterization using Remote Bias CFM. So first, a quick outline of what I'm going to be presenting today. I'm going to be showing you what exactly is remote bias electrostatic force microscopy, some motivation into why we want to use this technique, some of the models that I used in COMSOL multiphysics, as well as the test structures that we were interested in, some of the results I got, as well as just some conclusions I want to show. So electrostatic force microscopy is in itself an implementation of non-contact AFM or atomic force microscopy. This method is able to indirectly measure the work function of a sample by putting some sort of bias or signal onto this microscopic cantilever and scanning it over some sample of interest. And it does this by minimizing the force that is felt by the cantilever, which is a function of this delta V here, which in itself is a function of the voltage at the tip sample, as well as this VCPD, which is a measure of the difference between the work functions of the tip and sample. This technique can be used to characterize electrical properties as well as the topography of samples, and is especially useful in materials research today. So remote bias CFM, as the name implies, is a variant of EFM where the bias is placed not on the cantilever itself, but the test structure, as you can see on this screenshot that I got from my COMSOL simulation. This technique can be used to measure buried charge, as well as the force that we were talking about in the previous slide. And the long-range electromagnetic forces allow for characterization of not just surface structures, but subsurface structures. Why are we interested in this technique? Well, as in the past few decades, integrated circuits have been getting smaller and smaller, and the interconnects are starting to become, are starting to reach a limit of a few atoms wide. So manufacturers and fabrication labs are starting to investigate new paradigms for constructing ICs, specifically three-dimensional integrated circuits. However, we still need ways in order to test and verify that these structures are working accordingly. So that's why we want to use remote bias CFM to characterize these structures. So some of the specs that just going over some of the specs that I had to use in my simulations. Here I am going to show you just the different types of tips that I used. There's a symmetric tip, a leading tip where this front edge is perpendicular to the back edge of the cantilever itself, and a trailing edge where this edge is perpendicular to the front edge of the cantilever itself. And these are all modeled after a common Bruker probe that you can find online. Some of the test structures that we're interested in were a very simple single strip experiment, adjacent double strip experiment, as well as interdigitated multi-strips. For the sake of time, I'm only going to be showing you the results of this single strip experiment here. Some additional specs that I was able to investigate were changing the substrate in which the actual test structures were embedded from silicon dioxide to hafnium, as well as the tip radius itself and the cantilever angle at which we scanned over the test structure. So here I have the potential of the tip separated by the bias of the test structure from left to right, as well as on the same plot, different depths at which the test structure was embedded. As you can see, the potential doesn't exactly drop off very significantly, dropping on the left, we go from about 3.8 to 2.4 volts from max to min. Closer to the surface, the peak signal drops at about 0.5 volt per micrometer as we go further into the substrate. And further into the substrate, it drops to about 0.2 volts per micrometer. Here I separated them according to different tip geometries, as well as adding in the result of changing the substrate for the symmetric tip. As you can see, from the green, red, and orange lines, the peak actually shifts with the shape of the tip, which is reminiscent of my colleague Karthik's results. As you can see, as we get further into the substrate, the peak signal begins to decrease significantly, except for the hafnium, except for the signal that's embedded in the hafnium substrate. So as you can see, the hafnium dioxide actually propagates the signal pretty efficiently. So as a result, or in conclusion for this, yes, we can detect pretty shallow subsurface structures using common silicon dioxide. Some other results I wanted to show everyone were the results of the force measurement on the cantilever itself, separated again by both bias on the actual strip as well as the strip depth itself. As we noted in the previous slide, the actual shapes of these plots are similar regardless of the bias on the strip itself. The force measurement actually drops off a lot more significantly, making it a good candidate to measure full width at half max. And as like I mentioned, the actual shape of these are pretty independent of bias, except that these are scaled versions of each other. As you can see, there's some anomalies going on here at closer to the peak of the signal. That probably just has to do with like meshing or coarse scan parameters. So in the future, we'd probably just use a finer mesh or a finer scan parameter in order to alleviate these anomalies. So just to conclude, yes, we can characterize a single bias strip beneath the surface up to a certain depth. Some results from some conclusions that we made about the double strip is that we can distinguish between two adjacent bias lines up to a certain depth and proximity. And for the interdigitated multi-strip experiment, the conclusion was that how you bias these actual strips greatly affects how well you can resolve the actual test structure. Some future work is just including more realistic strip liners, as well as changing up the substrate, create a more directed parametric space, because sometimes these simulations take hours on end. So because of such a large parameter space that we're going over, and also adding effects of impurities within the actual materials by doping some of the materials. Some other future work is probably automating the data extraction and plotting, because COMSOL doesn't have the best plotting software. And lastly, I would just like to thank my advisors, Joseph Kapansky, as well as Dr. Yao Obeng and my colleague Karthik Rao for this great summer. And thank you, SPS, for supporting all of us this summer.